How do we drive single qubit gates on many qubits with microwave signals? First, we have to generate a signal for each qubit, which defines the duration and the amplitude of the pulse that we want to generate. Then, we multiply each pulse with the output of an oscillator at a well-defined frequency and phase that keep track of the phase of the qubits. After that, we combine all those signals together, and all this is done in the digital domain. We apply the signal to a digital-to-analog converter that converts the signal in the analog domain. We then multiply the resulting signal with a microwave high-frequency oscillation to move it to microwave frequencies, so that the generated pulses match the Larmor frequency of the different qubits. In that way, we obtain a spectrum comprising the spectral contents for each of the qubits. Since the Larmor frequency of each qubit is slightly different, we can use a single coaxial line to transmit this signal to our quantum processor. It is important to remember that a separate oscillator is needed for each qubit to keep track of the phase of each qubit. The microwave drive for each qubit will need a certain bandwidth BW. If we target n qubits, the total required bandwidth is n times the bandwidth of a single qubit. Now, considering this total bandwidth BW, according to the Nyquist criterion, the digital-to-analog converter needs a sample frequency that is double the bandwidth BW. Suppose that the bandwidth of each qubit is 10 MHz. If we have 100 qubits, we will then need a total bandwidth of 1 GHz, which means that the DAC has to be sampled at a rate of 2 gigasamples per second. We can conclude that even without considering any spacing between the qubits, we will need a very fast DAC, which gets very close to the limits of today's technology. How can we improve on that? One solution could be doubling the amount of digital cells. As shown here, in the top cell, we generate our pulses using a sine wave. In the bottom cell, we generate the same signal, but with a cosine wave. After that, we sum up the signal for the qubits and we convert them into the digital domain using two digital-to-analog converters, but sampled at the sample frequency equal to the bandwidth of our system. The final important step is to multiply the top signal by sinusoidal signal, and the bottom signal by a cosinusoidal signal. We implement what is called an IQ modulator. We build the in-phase path using the sine and the quadrature path using the cosine, and we sum them up together. In this way, we can generate exactly the same signal as before by proper cancellation of the unwanted signal on the two sides. Now, we only need digital-to-analog converters with a sample rate that is half of the sample rate required in the previous system. In this way, we are much farther from the limits of today's technology, at the cost of doubling the system size and introducing both sine and cosine oscillators, but this can be implemented. Of course, one thing that we should not forget is that after any digital-to-analog conversion, we have to place an anti-aliasing filter, shown here for completeness. Now, we have an architecture that can be used to drive multiple qubits via one single coaxial cable. But what are the challenges in this implementation? First of all, this kind of approach is called FDMA, Frequency Division Multiple Access, because we are using multiple frequencies to propagate signals for different channels. Now, the first challenge is that we need to provide a wide bandwidth to be able to feed all our n qubits into the coaxial cable, as we have seen before. Next to that, since we are targeting multiple qubits in the same wire, we have to make sure that when driving some qubits, for example the two qubits shown here, we don't produce spurious tones at other frequencies that could generate rotation on other qubits. We must keep our spurs low enough, or in other words, we need to keep a high spurious free dynamic range, or SFDR. The SFDR is nothing else than the difference between the tone that we generate and the unwanted tone that appear in the spectrum. Next, we have to take care of the shape of our pulse. In fact, until now, we have used rectangular pulses. which means that we start the microwave signal at a given time, we keep it constant in amplitude, and then we stop it. This means that the envelope is a rectangular envelope. As we know, the spectral content of such an envelope is sinc-shaped and has a very low decay in frequency. What is going to happen is that the energy of our signal targeting qubit 1 could go and leak into qubit 2, generating some spurious rotation there. This effect can be quantified as shown in this plot, where we represent the infidelity, 1 minus the fidelity, of a qubit adjacent to the qubits we are targeting, as a function of the frequency spacing. Of course, the closer we are to the target qubit, the more unwanted energy we get, thus the more infidelity. That spacing is proportional to the Rabi frequency at which we are rotating the qubit. In this example, if we want to keep the infidelity below 10 to the power minus 3, that is a fidelity of 99.9% with a rectangular pulse, we need to space our qubits 30 times the Rabi frequency. For a Rabi frequency of 10 MHz, this would be 300 MHz, which is a wide frequency. A better approach would be to use a smoother shaping of our pulse. Smoother in the time domain, for example a Gaussian pulse, means a much narrower spectrum in the frequency domain. For example, if using a Gaussian envelope, we can achieve the same target infidelity of 10 to the power minus 3 with only 4 times the Rabi frequency. So, for a 10 MHz Rabi frequency, we go from a 300 MHz spacing to only 40 MHz spacing. In that way, we get a much better pegging of our qubit frequency. Supposing that we are still using a Gaussian pulse, so that the energy of our qubit is very well limited, there is still an effect causing a shift of the Larmor frequency of nearby qubits, by a factor, for example, of delta f. Since the qubit that is rotating during this time is rotating at a different frequency, it could accumulate a phase error. Our electronic driver needs to keep track of this and compensate for such accumulated phase. Now, let's look to a practical implementation of the system we have described so far. As we have seen, the system will have a digital section and an analog RF section. In the digital section, we have an array of oscillators that needs to keep track of the phase of each qubit. Each of these is implemented with a numerically controlled oscillator, or NCO. We just keep track of the frequency, so we keep counting the phase in a cyclic manner. Then, depending on which qubit we target, we can multiplex, that is, select one of the phases. And the first thing we can do is a phase modulation using data from a memory. This is an extension of what we have seen until now. Using two lookup tables, one for sine and one for cosine, we can generate the sine and cosine of that phase, and we multiply those signals by the amplitude that we want for these two channels, the in-phase and quadrature channel. Both the phase and the amplitude information are provided by memory that could be on chip. In this way, we have the maximum flexibility regarding the pulse shaping. Next to that, we have the Z correction. As we mentioned before, this is nothing else than an additional phase correction that we can apply just to compensate the phase of a qubit, due to the driving of a nearby qubit. In the analog RF section, the functionality is very simple. We just take these two digital signals, the in-phase and quadrature signals, and we convert them to analog with digital to analog converters, we filter with anti-aliasing filters, and we up-convert them to microwave frequency with a Q-mixer and oscillators. Lastly, we send the output into the coaxial to the qubits. Let's now have a look at the experimental demonstration of the system that we have described until now. In this chip, called Horse Ridge, we have implemented this diagram, where we have an array of 32 NCOs followed by an IQ analog transmitter. In addition to this green block, which also contains an instruction memory, so that we can play different rotations one after each other. The analog RF section is shown here in details, and the chip has been implemented in Intel 22nm FinFET technology. The micrograph is shown here as well. This full chip was able to operate at 3 Kelvin, very close to the temperature of the cryogenic qubits. We call this technology cryo-CMOS because it's a CMOS technology but operating at a cryogenic temperature. This chip was able to generate waveforms with different amplitudes. We can observe on top, in the time domain, microwave signals with cosine, raised cosine, rectangular, triangular, and Gaussian envelopes. Below, we see the relative spectrum, demonstrating, for example, how the spectrum of a rectangular pulse is much wider than the one of a Gaussian pulse. And of course, the next step is showing how we can use these signals, generated by the cryo-CMOS chip operating at 3 Kelvin, to drive qubits. In this example, we have used a double quantum dot system with 2 qubits, Q1 in blue and Q2 in red. They are spaced in frequency, as we can see from the diagram, and our chip was able to drive a Rabi oscillation on each of the 2 qubits. We can see in red the Rabi oscillation for qubit 2 and in blue for qubit 1. We were also able to do gate tomography, as shown on the block sphere, demonstrating the rotation from the 0 state to the 1 state for one of the qubits. But how accurate is this control? To quantify that, we can do a randomized benchmarking experiment. In this plot, we show in blue the spin-up probability as a function of the number of gates applied in a randomized benchmarking experiment, using the room temperature equipment. In orange, we show the results for the same experiment by using the cryo-CMOS controller. Notice that in this plot, we have shifted the 2 curves for the sake of visualization. From those data, we can extract the fidelity of the operation and show that the achieved fidelity is the same within the error margin. These results demonstrate that the fidelity is not limited by the horse-ridge chip. And this was achieved by properly sizing the specification of the electronics and, consequently, the specification of the microwave signal to minimize the errors. Another interesting experiment is to operate 2 qubit gates using the same microwave signals. This can be done in the following way. If the coupling between the qubits is off, you get that driving each of them will be independent of the state of the other. If we activate the coupling between the 2 qubits, we get that the frequency to excite each of the 2 qubits depends on the state of the other. We can then use 4 different frequencies to implement 2 qubit gates, where the rotation of 1 qubit depends on the state of the other qubits. Details can be found in the reference paper here. With our microwave signal, we have now implemented both 2 qubit gates and single qubit gates. We can put all of this together to run a real algorithm. For example, here we run the Deutsch-Jozsa algorithm using real qubits and our real cryogenic CMOS microwave driver. In this algorithm, we try to identify in one shot whether the function we have is balanced or not. We have 4 different implementations of the function UF. 2 are balanced on the top, and the other 2 are constant on the bottom. And once we have run our algorithm, applying exactly those microwave signals we have described before, we measure qubit 2. We observe on the top that the state of qubit 2 has a high probability to be equal to 0, which means we have a balanced function, while on the bottom, we see that qubit 2 has a high probability to be in state 1, which means we have a constant function. This proves that we can run the full algorithm using microwave signals generated by an electronic driver operating at cryogenic temperature.